All right, this is from the 2021 BC test, and this is question 6. The function g has derivatives of all orders for all real numbers. The Maclaurin series, that just tells us it's centered at 0, for g is given by g of x on the interval of convergence. State the conditions necessary to use the integral test to determine the convergence of this series. Use the integral test to show that. Okay, so if we want to use the integral test, we first need to say that whatever this is positive, continuous, and decreasing on the interval. So on 0 to infinity, 1 over e to the x, which is equal to e to the negative x, is positive, continuous, and decreasing. This means you can apply the integral test. Okay, do we believe it's positive? Yes, for x equals 0 and above, e to the x is positive, so therefore 1 over e to the x is positive. E to the x is an increasing function, so 1 over e to the x would be decreasing. And it's continuous because e to the x is never equal to 0, and that's the only thing that would cause a domain issue. So we know we can use the integral test. So we need to look at the integral from 0 to infinity of that function. Well, first thing we notice is that it's improper, so we have to take a limit as b goes to infinity of that. So instead of putting infinity in the integral, you need to get infinitely close to it. So you're going to send a constant b to infinity. So now we're going to integrate that. Now remember, when we integrate e to the negative x, it's really a u substitution. So u would be equal to negative x. So du is equal to negative dx. So we're going to have a negative out in front. Oh, we just integrated it. Sorry, didn't mean to write that again. We put the negative out in front, and then this would be net e to the negative x evaluated from 0 to b. And now we plugging in our endpoints, we get minus the limit as b goes to infinity, e to the negative b minus e to the 0. Well, we know e to the 0 is 1, so we currently have the limit as b goes to infinity of e to the negative b minus 1. But thinking of e to the b, so this would be 1 over e to the b. We know e to the b grows exponentially as b goes to infinity, so the ratio of those is going to decrease to 0. So this is going to be equal to 1. Now, since this is finite, that says the integral converges. So by the integral test, the series also converges. Now, I don't think most of us would have approached this with the integral test. I think most of us would look at this and say, oh, it's geometric because we can rewrite it as this. R would be 1 over e, which is less than 1, so that's geometric converges. But they asked us to do the integral test, so we must do the integral test or you'll get no points. Part B. Use the limit comparison test with the series 1 over e to the n to show that the series g of 1 converges absolutely. So remember what it means to be convergent absolutely. To show convergent absolutely, we're going to look at the absolute value of this series. So when we look at the absolute value of that series, all that's going to do is get rid of the alternating. Now, for the limit comparison test, you take the limit of any two series. So I'm going to choose 1 over e to the n, and you're going to do the ratio of these. Multiply by the reciprocal to make it look a little bit nicer. We don't like complex fractions. So this limit, basically we're going to think that the degrees are equal because we have e to the n up here, e to the n up here. So it's going to converge to the ratio of leading coefficients, which is 2. Now with the limit. Now what the limit comparison test says, as long as this is not equal to 0 or infinity, the series will either converge or diverge together. So since the limit of the ratio is finite and non-zero, and we know that 1 over e to the n converges, the other one must converge also. And this is in absolute value. And that's all you need to say. I guess what you might need to say is that this converges in absolute value. Converges absolutely. Okay, so the next part C, determine the radius of convergence for the Maclaurin series. So remember, to do the radius of convergence, we look at the ratio test, unless it's geometric. So we're going to look at the ratio test. And remember, our goal is always to get x minus c less than r. This right here is your radius of convergence. So the limit as n goes to infinity, a n plus 1, replace all the n's with n plus 1. Then we're going to divide by the original one. Multiply by the reciprocal. After that, you're going to try to cancel everything that you can possibly cancel. So first thing I notice is that it's alternating, but I'm in absolute value, so the alternating does not mean anything. I also notice that there's x's on the top and bottom. Now the one thing that's kind of will mess up with a lot of people is that here we can't cancel that e to the n and the e to the n plus 1 because it's sharing a plus sign, it's not being multiplied. But if you look at those, now the degrees are equal. Okay, let's rewrite this piece. I think it'll make it a lot easier for us to see. So let's see, this gives us the limit as b goes to infinity. On top, we're going to have x times 2e to the n plus 3. And on the bottom, 2en plus 1 plus 3. So looking at that, we're definitely going to have the absolute value of x left on top. And looking at these pieces right here, it's going to leave us with an e on the bottom. And this is the thing people always get kind of confused on. This is the ratio test. If we're doing the ratio test, this needs to be less than 1 for convergence. This is what the ratio test says. Less than 1 convergence for ratio. So we know then that the absolute value of x minus is less than e, and that tells us the radius of convergence equal to e. Part D. The first two terms of this series are used to approximate g of 1. Use the alternating series error bound to determine an upper bound on the error of the approximation. Okay, so they specifically asked for the upper bound. All right, so I'm going to first write out a couple terms of this series. So our first term would be when n equals 0. So you're going to have positive 1 over 5. If we plug in n equals 1, we're going to get negative 1 2e plus 3. And I'm going to plug in another one, n equals 2. I'm going to get a plus 1 2e squared plus 3. Now it says I'm going to use the first two terms, which means I'm going to truncate it right here. For a convergent alternating series, the error is less than the first omitted term. So we know that the error is going to be less than 1 over 2e squared plus 3. Remember, error is always positive, so if it was negative, you make sure you take the absolute value of it. Now they want us to